All right, question one normally is pretty easy, so shouldn't have too many problems with this. Let's start with option A. This graph has 7 vertices. Yes, look, 1, 2, 3, 4, 5, 6, 7. That is true. And we're looking for not true. There are no isolated vertices. An isolated vertex would look like that. We don't have one of them. So there are none. Correct. All vertices have an even degree. This one's got 2, 2, 2, 4, 2, 2, and 2. You just draw a little circle around it. You cross 2 lines. This one you cross 4 lines when you circle around the vertex. So those are all even numbers. That is true. Then 6 of the vertices have the same degree. That is true. There's 6 with 2. And if we add them all up, though, we actually get 16. So that is not true. So the answer is E. All right. The minimum time taken to complete the entire puzzle. It looks like we're allocating jobs, doesn't it? And that means we're going to be doing Hungarian. So this one looks fairly simple, actually, if you look at it. Let's do our row reduction. Audrey, everything is 5 in her row, so they're all 0. So we're going to take a line to cross out all those zeros. Bruce, 3. So his lowest number here is going to be 0, 4 minus 3, 1, 5 minus 3, 2, and 6 minus 3, 3. Christy, her lowest number is 3. So 6 minus 3, 3, 2, 1, and 0. And Darren takes 5 on everything. So 0, 0, 0, 0. And if you try and do your lines, let's do that in green. Look, I've got to do one line. Oh, that's not green. Having some pen fails here. There we go. If you do that in green, it takes 1 line, 2 lines, 3 lines. Oh, we've got to have 4 lines. Okay, so it's going to be 4 lines. We can go straight to allocating. And so if you think about this, Bruce has only got 1 0 in his row. So Bruce gets part 1. Christy has only got 1 0 in a line, so Christy gets part 4. And then Audrey's got lots of zeros, Darren's got lots of zeros, so they can get either one. So Audrey could get part 2, and Darren can get part 3 if you like. You have to go back to the original values, so I'm going to just scrub everything off here. And we can see what the actual numbers were. So the actual numbers were Audrey's always going to take 5, Bruce is going to take 3, Christy's going to take 3, and Darren is going to take 5 for those activities. Just to remind you, A to 2 is 5, B to 1 is 3, C to 4 is 3, and Darren to 3 is 5. But you know, if you're actually quite logical on this thing, whatever Darren does is going to take 5. Whatever Audrey is going to do is take 5, and you might as well give the lowest one of Bruce to part 1, and Christy the lowest part to part 4. You probably need to do Hungarian to see, oh, that's a 3, that's a 3, and they can have a 5 and a 5. It was going to add up to 16. But it's always good to just double check this the slow way. And so B, 16 is the correct answer for number 2. Okay, good multiple choice question to check if you know all about trails and paths and cycles and circuits and Hamiltonian and Euler. Remember, I always say Euler is every edge. So I remember it's all about the E's for Euler. That's how I try and remind myself. Now, we've got to look up the idea of trails and paths are generally they're much easier than circuits and cycles, yes? So whatever you're doing, you're going to be returning back to what you want to do. Now, it's quite obvious that with Euler, you're not going to be able to get back to F. The F is actually what F's up everything for this. So Euler circuit says you can have no odd degree vertices, and immediately F has a degree of 1. So you can't do Euler circuit. Now Euler Trail says you're allowed 0 or 2 odd vertices. And if you look, this one's 2, this one's 2, this one's 4, this one's 2, and this one is 3. So you could do an Euler Trail. So Euler Trail, we can do, I'll highlight then. So Euler Trail, yes. So Euler Trail, yes, but Euler Circuit, no. So we have ruled out D and A. Now Hamiltonian Path, that is the ridiculously easy one. Hamiltonian Path is just going round to every sort of town when he was touring Scotland. So there you go. There's one. There's plenty of others. So Hamiltonian Path, we can do that. We've already eliminated D though because of the thing. So Hamiltonian Path is Hamiltonian Cycle. Well, again, F is stuffing that up. We can't leap across there. There's no edge, so we can't do Hamiltonian Cycle, can we? So Hamiltonian Cycle's out. Hamiltonian Cycle's out. So that rules out C and E. The answer must be B. And that's kind of intuitive as well, because trails and paths, as I said right at the very beginning, are much easier than cycles and circuits. So it'd be very odd to have an Euler Trail and not an Euler circuit, or a Hamiltonian cycle and not a Hamiltonian path. That's just a bit odd. Now it looks like we have to do the big performance of a critical path, because it's saying we've got a minimum time to complete this project, and we want to know the activity that has the LST of 12. Now remember, when you're doing LST, that's when you got your boxes, and I normally do the forward pass in a red number, and that's when you go have the max plus, and you're going that way. And then you normally do a backward pass, and you fill out the other box, and that's your minimum, and you're subtracting, right? But I'm just going to show you that this one's fairly straightforward, because there's only a limited number of paths you can follow for these activities. And the activities we're looking at for Iggy, Jen, Kai, Lee, and Mo. So the only paths you can do are this top one like this, then this, then this, then that, and then that. I'm just going to do the calculations just focusing on those endpoints sort of thing. There's not much room to do boxes, so I'll try and avoid doing that. I'm just going to do the red and green though colors. All right, so let's clean all this up and let's look at this. So do the top path, and you'll see that you've got 3 plus 5 is 8 plus 4 is 12. All right, let's do the next path, which is Bob, Ed, Jen. So this is one for Jen, and that's 3 plus 7 plus 5, that's 15. Then we do the next path, which is Bob, Fab, Kai, and we get 3 plus 5 is 8, 8 plus 4 is 12. Then we're going to do the next one, which is Cal, Gok, Lee. And if you add those up, that's 10. And if we do the next path, which is Cal, Hal, Mo, I am still speaking English, aren't I? 6 plus 2 is 8, plus 6 is 14. So that's our last path. What's our biggest red number? Our biggest red number is 15. So we know at the finish it's going to take 15 for the whole project. And all we've got to do is the sort of the minusing back. And we're only going back one step. So 15 minus 6 gives me for 9. 15 minus 3 gives me 12 for Lee. So that looks like that's the answer, doesn't it? But let's just check everything else. 15 minus 4 gives me to squeeze these numbers in. 15 minus 4 is 11. For Jen, 15 minus 5 is 10. And for Iggy, 15 minus 4 is 11. So it does indeed look like the correct answer is D, Lee, for question 4. Okay, so we need to do an adjacency matrix for this network and see how many 0 elements there are. Now, we'll do it the slow way, and then I'll talk about some of the quicker ways of this. So A, B, C, D, E, A, B, C, D, E. Doesn't matter where you put your letters. On the diagonal, you can't be friends with yourself. There's no loops from any of the vertices, so no weird things be friending yourself. There we go. So we know we already got 5 zeros. And then we got to think where A is connected to. So A is connected to B. So A does go to B. And that also means B goes to A by symmetry. A does not connect to C. And A does not connect to, oh, A does connect to D. It goes around the back here. So I've got a 1 there. And A does not connect to E, so 0. And so if you read across, that is the same, got to be the same down. So 0, 1, 0, 1, 0 is going to be 0, 1, 0, 1, 0. All right. So let's keep going with filling out this matrix. We've already covered some of the lines. So we're looking at B. B can also go to C, and by symmetry, this guy. And B can go to D. So B can go to D, and B can go to D, and B can go to E. So B can go to E. B's a very friendly person, he's friends with everyone by the looks of it. And then you can see on the diagram what lines are left. So C can go to D. So C can go to D, which means C. We get the 2 lines there, and then C can't go to E, so C can't go to E, and then E to D like so. So how many zeros have we got? We've got 5 on the diagonal, and then a 3 there, and a 3 there. So that's 11 if you add them all up. But think about this. Each line represents 2 numbers, right? So if you look at this, this 0 is partnered with this 0. And this 0 is partnered with this 0, and this 0 is partnered with this 0, because, you know, they're partnered by a line. So you've got 5 for the diagonal, but you've got 2 for every missing line, and there are a bunch of missing lines. There is A is not very friendly, so there's 1, we've already got the A to D line, 2, and where's our third line? So remember, A to C wasn't a line, A to E we've added a line, and C isn't connected to E like that. So 3 lines, each line represents 2, so that's 3 2s are 6. That also tells us another way of looking at this diagram.